Have you ever wondered if the night sky is just a ceiling of lights or a window into infinity? That curiosity, that urge to understand what lies beyond our world, is the origin of one of the oldest and most fascinating sciences, astronomy. Astronomy is the study of the universe beyond Earth. It explores celestial bodies like stars, planets, galaxies, comets, and nebulae, as well as the phenomena that occur in space. It doesn't just observe. It seeks to understand how the cosmos works, from the origin of time to the ultimate fate of the universe. Unlike other sciences, astronomy can't conduct lab experiments. We can't touch a star or trap a black hole in a box. We only observe, sometimes with our own eyes, other times with massive telescopes or orbiting satellites. And from that data, astronomers build theories to explain what they see. Astronomy doesn't work alone. It draws on physics to understand gravity and light, on chemistry to discover what stars are made of, on mathematics to calculate orbits, distances, and trajectories. It's also deeply connected to philosophy because ultimately, studying the universe is a way of asking about our place within it. Today, astronomy is a modern, technological, and precise science, but its roots go back thousands of years, when our ancestors looked up at the sky in awe, trying to unlock its secrets. In the following sections, we'll explore how this science was born, how it evolved through the centuries, and what discoveries have forever changed our understanding of the universe. To truly understand astronomy, we have to travel back thousands of years, to a time when there were no telescopes, no satellites, and no scientific method as we know it today. Back then, the night sky was not just a mystery. It was a guide, a clock, a calendar, and a source of wonder. The earliest civilizations, like those in Mesopotamia, Egypt, China, and Mesoamerica, observed the heavens closely. They noticed that the stars moved in patterns, that the moon changed shape over time, and that certain stars returned to the same position in the sky year after year. These observations weren't scientific in the modern sense, but they were incredibly precise. For example, the Babylonians developed detailed star charts and even predicted eclipses. The Egyptians aligned their pyramids with the stars, and their calendar was based on the heliacal rising of Sirius. In Mesoamerica, the Maya created complex calendars and tracked the movements of Venus with remarkable accuracy. Why did they care so much about the sky? Because it was essential to survival. The stars helped mark the seasons, which guided planting and harvesting. Eclipses and planetary alignments were interpreted as signs from the gods. Astronomy was deeply tied to religion, agriculture, and power. In ancient times, there was no real distinction between astronomy and astrology. Both were ways of reading the sky to understand the world and predict the future. It wasn't about science for science's sake. It was about meaning. But these early observations laid the groundwork for what would eventually become a scientific discipline. The sky inspired not only myths and rituals, but also questions. And questions, as we'll see, are the heart of astronomy. In ancient Greece, something remarkable happened. People began to look at the sky not just for patterns or omens, but for logic. They wanted to understand the cosmos through reason and mathematics, not just myth. One of the first to take this step was Thales of Miletus, around the 6th century BCE, who suggested that celestial bodies were not gods, but physical objects. Then came Anaximander, who proposed that Earth was floating freely in space, a radical idea at the time. But perhaps the most influential figure was Pythagoras, who introduced the idea that the universe was governed by mathematical harmony. His followers believed that the motions of celestial bodies followed perfect, invisible geometries, the so-called music of the spheres. Later, Plato and Aristotle refined these ideas. Aristotle proposed a geocentric model, the Earth at the center, with planets and stars embedded in crystal spheres revolving around it. This view, though incorrect, would dominate Western thinking for over 1,000 years. Then came Claudius Ptolemy, in the 2nd century CE. His book, the Almagest, compiled centuries of Greek astronomical knowledge into a complex geocentric system that could predict planetary motion with surprising accuracy, using a system of epicycles and deference. It wasn't simple, but it worked well enough to last for 1,400 years. Greek astronomy wasn't perfect, but it introduced critical ideas that the universe could be understood through logic, that the stars followed natural laws, and that observation and theory could work together. When the Roman Empire adopted Greek science, it preserved these astronomical texts, and through translations into Arabic during the Islamic Golden Age, they would later return to Europe, setting the stage for a revolution. A revolution that would begin not on Earth, but in the mind of a man who dared to move the sun to the center. For over 1,000 years, the Ptolemaic model dominated Western thought. Earth was at the center, the stars were fixed in place, and the heavens were perfect and unchanging. But in the 16th century, a quiet revolution began, one that would reshape not just astronomy, but science itself. It started with Nicholas Copernicus, a Polish astronomer who, in 1543, published De Revolutionibus Orbium Coelestium. In it, he proposed a heliocentric model, the sun at the center, with Earth and the other planets orbiting around it. It was a radical idea, not just scientifically, but philosophically. If Earth was not the center, what did that mean for humanity's place in the cosmos? The idea gained traction thanks to Galileo Galilei, who used one of the first telescopes to observe the Moon, Jupiter, and the Milky Way. What he saw contradicted the old models. The Moon had mountains and craters, Jupiter had moons of its own, and the Milky Way was made up of countless stars. The heavens were not perfect, they were dynamic and complex. At the same time, Johannes Kepler improved on Copernicus's model by discovering that planetary orbits were elliptical, not circular. His laws of planetary motion brought unprecedented precision to astronomy. And then came Isaac Newton, who in 1687 formulated the law of universal gravitation. With it, he explained how celestial bodies move, not because of invisible spheres or divine forces, but because of a single natural law that applied both on Earth and in the sky. This was the true birth of modern astronomy, a science based on observation, mathematics, and universal laws. It wasn't just about looking at the stars, it was about understanding them. From this point forward, astronomy would no longer be confined to philosophy or religion. It became a physical science, driven by evidence, powered by reason, and limited only by our tools and imagination. By the 19th century, astronomy had become more than just mapping stars and tracking planets. With the invention of spectroscopy and photography, astronomers gained powerful new tools that would transform the field forever. Spectroscopy, the study of light and its composition, revealed something astonishing. Stars are made of the same elements as Earth. For the first time, we could analyze the chemical composition, temperature, and motion of distant stars by studying their light. This marked the birth of astrophysics, the fusion of physics and astronomy to understand the inner workings of celestial bodies. Then came photography, allowing astronomers to capture the sky with greater precision and compare changes over time. This helped discover previously unseen objects, faint stars, nebulae, and even new planets like Neptune. In the early 20th century, another revolution was brewing. In 1929, Edwin Hubble made a discovery that changed everything. Galaxies were moving away from us, and the farther they were, the faster they moved. This meant the universe wasn't static, it was expanding. This expansion supported a bold new idea, the Big Bang Theory. It proposed that the universe had a beginning, a single moment billions of years ago, when all space, time, and matter emerged from a singular point. Suddenly, astronomy wasn't just about stars, it was about cosmic origins. Meanwhile, Albert Einstein's theory of general relativity offered a new framework to understand gravity, time, and space itself. His equations describe how massive objects curve space-time, predictions later confirmed by the bending of starlight and the precise motion of planets. As telescopes grew larger and more powerful, astronomers discovered distant galaxies, black holes, quasars, and cosmic microwave background radiation, the afterglow of the Big Bang. The universe was turning out to be far older, bigger, and stranger than anyone had imagined. The 20th century turned astronomy into a global, data-driven science and laid the foundation for a new era, one that would reach far beyond Earth. The launch of Sputnik 1 by the Soviet Union in 1957 marked the beginning of a new chapter in astronomy, one that would take us above the atmosphere and into space itself. For centuries, astronomers had observed the universe from the ground, limited by Earth's atmosphere. But with the arrival of rockets and satellites, we can now study the cosmos from orbit with unprecedented clarity and reach. In 1969, the world watched in awe as humans set foot on the moon. The Apollo missions weren't just about space travel. They were the ultimate expression of our curiosity, our desire to explore and understand. For the first time, we weren't just looking at the moon, we were standing on it. But while astronauts captured imaginations, unmanned missions quietly transformed our knowledge. Probes like Voyager 1 and 2 explored the outer planets, revealing active volcanoes on Jupiter's moons, giant storms on Neptune, and intricate ring systems around Saturn. Today, Voyager 1 continues to send data from interstellar space. In 1990, NASA launched the Hubble Space Telescope, giving humanity its clearest view of the universe. Floating above the atmosphere, Hubble captured breathtaking images of galaxies, nebulae, and deep space, and helped measure the age of the universe, confirm the expansion rate, and even detect exoplanets. Speaking of exoplanets, in 1995, the first planet orbiting a star like our Sun was discovered. Since then, missions like Kepler and TESS have found thousands more, many in the so-called habitable zone, where liquid water might exist. The question is no longer if there are other worlds, but how many and what kind. Today, space telescopes, planetary missions, and robotic explorers continue to push the boundaries of astronomy. We've mapped Mars in exquisite detail, flown past Pluto, and landed on comets. And with next-generation observatories like the James Webb Space Telescope, we're peering into the earliest chapters of the universe itself. The space age turned astronomy into exploration, not just of ideas, but of places. And it's only the beginning. As our tools grow more powerful, so does our understanding, but also our realization of how little we truly know. In the late 20th century, astronomers began noticing something strange. Galaxies were spinning in a way that didn't match the visible matter they contained. According to the laws of gravity, they should be flying apart, yet they weren't. Something unseen was holding them together. That something is what we now call dark matter. Invisible, undetectable through light, but making up roughly 27% of the universe. We can't see it, but we know it's there by the way it bends light and affects motion on cosmic scales. Even more mysterious is dark energy. In the 1990s, observations of distant supernovae revealed that the universe's expansion isn't slowing down, it's accelerating. Some unknown force is pushing space apart faster and faster. We call it dark energy, and it seems to make up nearly 70% of the universe. That means everything we've ever seen, stars, planets, galaxies, gas, dust, is just about 5% of the cosmos. The rest is unknown. And yet, even with so many unanswered questions, astronomy continues to advance. We've detected gravitational waves, ripples in space-time caused by colliding black holes and neutron stars, a prediction of Einstein, now confirmed by instruments like LIGO. We've captured the first image of a black hole in 2019, showing the glowing ring of matter around the event horizon in the galaxy M87. Proof that even light cannot escape these cosmic giants. We've mapped the cosmic microwave background with extreme precision, a baby picture of the universe, just 380,000 years after the Big Bang. And with missions like Gaia, we're creating the most detailed 3D map of our galaxy ever made, charting the motion of billions of stars. But the big questions remain. What is dark matter made of? Why is the universe accelerating? Are we alone in the cosmos? These are not just scientific puzzles. They are reflections of our deepest human curiosity. As we stand at the edge of the known universe, peering into galaxies billions of light years away, one thing becomes clear. Astronomy is far from finished. In the coming decades, new telescopes like the James Webb Space Telescope, the Vera-C Rubin Observatory, and the Nancy Grace Roman Space Telescope will deepen our view of space and time. They will look farther back to the first stars and galaxies, and more precisely, searching for Earth-like planets, studying dark energy, and detecting the fingerprints of life in distant atmospheres. Meanwhile, ground-based observatories are reaching new heights. Arrays like the Square Kilometer Array, SKA, will map radio signals from across the universe, while projects like the Event Horizon Telescope continue to sharpen our view of black holes. But astronomy's future isn't only about bigger telescopes or better data. It's also about collaboration between scientists, nations, and even the public. Citizen science projects are allowing people around the world to help classify galaxies, discover exoplanets, and track asteroids. And artificial intelligence is opening new doors, helping astronomers sift through vast amounts of data to find patterns, anomalies, and hidden wonders no human could spot alone. As we explore, we're also preparing to venture farther. Missions to Mars, Europa, and Titan may soon uncover signs of life, or at least the conditions for it. Private and public space programs are laying the foundation for humans to become interplanetary explorers. But astronomy isn't just about technology or discovery. At its heart, it's about perspective. It reminds us how small we are, a pale blue dot orbiting an average star in a vast galaxy among billions. But it also reminds us how special we are, intelligent beings capable of asking questions, building instruments, and uncovering the secrets of the universe itself. From ancient stargazers to space telescopes, astronomy has always reflected our desire to understand where we come from, where we're going, and what lies beyond. Because the night sky isn't just a ceiling of lights, it's a mirror to the infinite.